Is it fine?
Yep. Okay, so for those who don't know me, I'm Luca Andal, and I will report what we have done during this workshop about acoustic unit discovery. So let me first recap or give some motivation. One, we are interested in having some automatically derived acoustic units. And if you think about how are built any ASR system nowadays, we always assume some low-level discretization of speech in terms of phone, triphone, or syllables. And all this phone set or unit set for any language is kind of unique. So, for instance, British English has a slightly different phone set of American English. And if we want to, at some point, build some ASR system or whatever speech system for any under-resourced language, then we'll have to find a way to come to have to discover, to learn some phone set specifically for this language in order to reach good performance. So before to go in the models to see how we can actually learn some specific units for any language, let's talk a bit about how we will evaluate ourselves, how we will know that we are actually improving our system. So optimally what we would like to do is simply to have some phone set or to derive some phone set to build some ASR based on this phone set and to evaluate the phone error rate, word error rate, whatever metric is at the final task of the speech system. Unfortunately, it's not trivial, and maybe the technology right now is not mature enough to allow easily to build such a system. Instead, we have decided to evaluate ourselves with some correlation measure between, let's say, true or human transcription of phones and some derived units. So this is not the perfect way to evaluate ourselves, but it's cheap and it's a good alternative. It's a good alternative for now because we are not able yet to get the word error rate that we aim to. So this correlation measure is actually the normalized mutual information, and it has several advantages. The first one is we do not need to have to learn a phone set or acoustic unit set with the same number of phones. So you can still, if let's say that I have in English, I have let's say 60 phones, and I have a acoustic unit set of 100. This is not a problem. With this metric, I can still evaluate how good my units are to describe the original phone set. The second thing important to note is also that having 100 correlation with the true phones or the human phone transcription is not ideal neither, because we just want to have some discretization of speech, which is enough to build some ASR system. But we have so far no clue that phone is actually the optimal target. And as an example, we try to use this metric with the output of some ASR system, which were performing 23 phone error rates on TIMIT. And when we evaluated the output of this ASR system, and we just evaluate with the normalized mutual information, we got about 42%. So we see that even with a relatively low level of correlation between true phone and the output of some phone recognizer, we can still have a nice performance. So now let's talk about how we can do that. So there were different approach for performing this stuff, discovering some acoustic units inside the speech. But the one that seems to be very promising was proposed by Lee in 2012, and which is based on Bayesian model with some specific Dirichlet process prior. And the idea is as follows. So I don't know if, yeah, you can see the mouse. So I have a pointer. I have a manual pointer. Okay. So this line, all these variables just represent HMM. So far nothing fancy. And the idea of Lee is that we can eventually learn clusterize the speech in a set of HMM. So each unit would be represented by a HMM, as it is done in standard ASR. And we would like to cluster the speech based on this HMM. And the way we segment the data is slightly different as one would expect. So she has some binary variable for each frame of the speech. And if this binary variable is switched on, is 1, then it just means that there is the segment is ending here, and the next frame, at the next frame is going to start a new unit, new phone or new segment. So this is this binary variable represents the segmentation of speech, and this prior over the weight of the mixture of HMM and prior over the parameters are defined by is modeled by a Dirichlet process prior. So the specificity here is that this prior assumes an infinite number of components inside your mixture. So the idea is as follows: we'll try to cluster the speech with an infinite number of units, but we know that, or we hope that, as the result of the training, only for generating the speech, only a subset of this cluster were actually used. So the idea of having an infinite number of cluster at first is just to say, okay, now when I train this model, I want to train the acoustic parameter of the HMM, but I also want to learn the complexity of my mixture. I want to learn how much components do I need to properly model the speech. So this kind of model performs two things: acoustic modeling and complexity learning, which is kind of suitable for our task. There are some limitations, though. The first one is, as I told about this boundary frame, which is it's kind of hard to train, because it's actually this evaluation of boundary frames to evaluate if for each frame, if this frame is a boundary frame or not. It makes the whole training very slow. And also the Gibbs sampling, which is used to evaluate the other parameters, the HMM, basically the parameter of the HMM, is also inherently slow because of its sequentiality. So all these problems or limitation makes this model very hard to apply for large speech database. And the problem of speech technology is that it requires large scale database. So in order to make this model applicable for real life scenario, we needed to improve its performance and its scalability. So the idea was, instead of having this, first we just made a couple of changes to this model, and the first thing we did was to just get rid of this binary variable, which was more annoying than helpful, and just seeing our mixture of HMM as a single big HMM, kind of phone loop model, without binary variable. And now if we want to decode or segment the speech, we just have to run the forward-backward algorithm, and we can just get the most likely sequence of units and segment our data like this. The problem here is we still assume that we have some Dirichlet process prior on top of this phone loop model. So here I just drawn 3 units, but just imagine that this is HMM with an infinite number of units. So the training with such HMM is not straightforward. So to make it fast enough and achievable, we had to use some approximation, namely versional inference, and that was actually a good thing to do, because when we compare on a toy experiment which one of the versional base or the Gibbs sampling version of the model perform better, we see that the versional base, though it's approximating training, give a much better accuracy in a smaller training time. So just this is about 10 iterations of training. For the blue line, because the versional base can be easily parallelized, it was about 1 hour. According, of course, of the number of threads or jobs you allow. Whereas this red line, the Gibbs sampling version, these 10 iterations are about 10 hours of training, because it's not easy to parallelize. So that was a good achievement, because we had now some model, Bayesian model, to cluster the speech into a set of acoustic units. And this model can be trained and applied to large speech database. Now let's of course, here it's kind of number which are not very explanatory about what kind of units are learned. So we did a couple of experiments or a couple of analyses on our data to actually try to understand what kind of units are learned by this model. So the first thing we plotted is the duration of units learned by this model. And so the green one, I would get my manual pointer. So the green one is the true segment, the true phone estimate, and you see that it basically runs from 0 to 200 milliseconds, and kind of most of them are before 100 milliseconds, but still you have a long tail or heavy tail until 200 milliseconds. Whereas the acoustic units are more, so there is no zero because we just, we don't allow any units to be smaller than 2 or 3 frames. But most of them are actually concentrated to this area. So we see that in general, units that we learn are kind of smaller than the true phones. We then look at the distribution of phones. So the green, once again, the green dots are the frequency of each phone in the TIMID database. And you see that it follows this nice exponential law, whereas the derived units exhibits kind of flipped sigmoid or flick S line. So we see that we have some model, it learns something, but it's definitely not exactly phone. But it doesn't really matter that much because once again, we don't want to learn phone. We don't want to be wizard and to guess what the phones are. We just need to have some discretization of speech, segmentation of speech, to find some subworld units that are anyway helpful and to build any ASR system. So here are a couple of examples of what are these units. So we just took the units defined. So we ran some the Viterbi decoding on TIMID, and we just pick up some units that were defined by this segmentation. No.
Look like this one.
So while Sanjeev is setting this up, I just got a message from Hamza from BUV. He says there are 8 people watching from there, and till now it has been pretty much more entertaining than the Czech team performance in European Cup.
I don't know why this audio is not.
I agree.
Okay, go ahead and try. Yeah, okay, now we'll have to. Okay, go ahead.
No. Is it the right cable?
Go into the right cable. Let's go into that one.
Wait, am I plugged at the correct place also? It seems so. Is this one? Or? To the right, the jack. You hear?
Which audio port on the PC?
On the right side? Yeah, this one? Okay, so trust me, they are nice when you hear them. So, I don't know, let's move on. So, another question that we may ask is we started with some Bayesian model. It's kind of complicated to train. We need to have some approximation to be able to train it. So what would it be if we just assume simpler model, just take some standard ASR system, like maximum likelihood solution, and we don't try to learn how many units are there. We just fix the number of units and what's going to happen. And so this, the experiment was done by Shinji. And so this compares the NMI on a Wall Street Journal between the Bayesian IUD, so this is the model I just introduced, and the maximum likelihood AUD, so this is just a mixture of HMM or trained with Kaldi. So you have just a monophone system and context dependent. And we see that actually there is quite a nice difference. There's quite a lot of difference between the trained model. So this comparison, it's not 100% fair because I train with a proper forward-backward algorithm, whereas this one is just trained with a Viterbi approximation. So that may explain also such an important gap. But anyway, it seems that being Bayesian and being careful about the training, being exact, seem to be quite important. So Bayesian, it's cool and it's useful. Okay, so now if you look, once again, we looked a bit more about what's the unit we got when we have the same sentence spoken by two different speakers, and we hoped that actually we would like to have almost the same units. because it's the same speech. We would like the unit to learn just the phonetic variability, not the speaker variability. But when you look at this, so this is the same sentence spoken by two speakers, and we see that it's not that great. I mean, we have some mapping. So all the white parts are matching parts, the blue part are substitution, and this is insertion. And so we still have some overlapping, but we have also a lot of variability and a lot of substitution. So this is problematic if we want to go further in our task of building ASR for low resource languages. We would like to have some phone set which is kind of coherent, robust, and stable over a speaker variability. So the idea here during the workshop was that maybe we can reduce this variability by constraining our model and to apply some phonotactic language model on top of the unit. So this is how it looks like the model now. And we say that, okay, now I have trained some acoustic units with this nice Dirichlet process prior. So I have some model trained, but now I would like to constrain the model more to be able to reduce this, as I mentioned earlier, this variability. So the idea here is say, okay, now let's get rid of the Dirichlet process prior and assume that I have a fixed number of components because I learned them already. So I know how many components I have in my data. So I will just have some prior over the parameter of the HMM, and this prior is the number of parameters is fixed now. And instead of having a Dirichlet prior over the weight, no, I would put some hierarchical Pitmanier process language model on top of the unit. So here it's not anymore a mixture, still a mixture, but slightly more complex because I do have some probability. I do take care of the fact that if I have some unit A1, then it can be followed maybe by A10 or A20, but almost never by A30. So I constrain my model in such a way that I would put probability over the context, over the sequence of units. The slight problem here is I used to train this model with variational base, but once you replace the Dirichlet process prior with the hierarchical Pitmanier process language model, then it's not anymore trainable with variational base. I'm running out of time. So instead, we just use a Viterbi approximation. And we estimate the best path and we estimate the acoustic parameters on this best path. So here are the results. So this is a training over TIMIT. So you see that all this part is a training with a standard model with a Dirichlet process prior. And at this point, we say, okay, now I assume that the model is trained enough, and I just want to use the phonotactic language model. And you see that it nicely escapes from this local maxima. And we compute it over different databases, so TIMIT and Wall Street Journal, and also with different features. So here it's Wall Street Journal with multilingual bottleneck features. So Leda will talk later about this. And we see that whatever the data and whatever the features are, we still get about the same improvement, about 1%, slightly more than 1% in NMI. So this leads me to the end of this talk. And here are the takeaway message. Basically, acoustic unit discovery is challenging, but it's also important that if we want to reach a lot of language that we do not have any linguistic information about them, we need to have this building block in our system. So this is challenging, and this is also important. We have reached some improvements during this workshop, but if you look at the baseline, the top line, about this amount of NMI on TIMIT, this is to have some proper and accurate model. Even though we got some improvements, we are still far. We are not so far. Still a huge gap to reach for our model to be very useful. And as the last experiments show, we see that we can actually improve the accuracy of the model just by using the context information. So it can be phonotactic, and you will see later, Thomas will talk about also reusing the context from words, from discovered words. So this is, I think, one promising track to improve the accuracy of automatic unit discovery. That's all.